Okay, so I want to talk about a small generalization of a previous observation that we made. We had been considering this Poncelet family here, uh, inscribed in an external ellipse, the black ellipse, and circumscribed about a fixed brown incircle. So therefore x1, its incenter, is stationary over the family. Now, in the previous video, we showed that uh, if I drew the excentral triangle to this family, so let's see it here, the excentral triangle, shown solid green. If I drew the family of excentral triangles, and if I let each one of its vertices, the excenters, specify the centers of three circumellipses. So let's draw, for example, one of the circumellipses. Here it is. Let's scale this out a bit. So here's a circumellipse, this orange ellipse. It passes through the three vertices of the Poncelet family, and its center is one of these vertices here. Since this is the excentral triangle, this is called an excenter. Now I can first of all animate this, and notice first of all that the area of the circumellipse is variable. Okay. However, when I draw the three like-defined circumellipses shown here, each one of them having a center on a distinct excenter, we get this interesting result that the sum of their areas is invariant. Okay, so this video is about trying to generalize this to other concentric Poncelet pairs. Let's look, for example, at sort of the dual of this pair, which is called the pair with the circumcircle. So let's turn this thing off and let's go to the pair with the circumcircle. What is this pair going to look like? It's inscribed in an external fixed circumcircle, this black thing, and it circumscribes a fixed internal ellipse. So let's watch this family. It's a rather interesting family, somewhat dual to the previous one, right? I can make this guy a bit more eccentric. So this is what you get. So this family has a bunch of conservations that are not germane to this video. Now, let's go ahead and draw the excentral triangle of this family. There it is. There's the excentral triangle. And I can try to play the same game. Let's draw a circumellipse that obviously passes through the three vertices of this family and passes through one of the excenters. Well, the circumellipse has, as before, a variable area. Let's draw the three of them now. Here are the three circumellipses. Let's scale this out. We can see that their areas are distinct. However, the sum of their areas is not invariant. Okay, so this is a downer. But here is the key to this. Let's go back to the first example. We're going to go to the pair with the incircle. Here's a pair with the incircle with its three circumellipses. And when we did the construction of three circumellipses centered on the excenters, the sum of the areas was constant. Right? So this is our previous result. Now let's observe something very interesting about this pair. Let's turn off the ellipses, and I'm just going to maintain the excentral triangle. Let's make the system less eccentric. Let's make it bigger. Now, what is the excentral triangle? The excentral triangle happens to be the anticevian triangle of this blue family with respect to x1. Let's draw the three cevians of the excentral triangle through x1. Notice how these three cevians meet the reference triangle, this three-periodic reference triangle, at its vertices. So you could say that the excentral triangle is the anticevian triangle of the three-periodic with respect to x1. Anticevian in the sense that if I did the opposite and I said, what's the cevian triangle of the excentral with respect to, in this case, its orthocenter, which happens to be the incenter of the reference triangle. So the cevian of the green triangle with respect to x1 of the three periodics, or x4, not shown here, congruent of the green triangles, the cevian is the blue triangle. So The green triangle, the eccentric, is the anticevian of the blue. Okay, so when I do the ellipse construction, the 3-ellipse construction with respect to the vertices of the anticevian of x1, I get a constant sum of areas. Let's go back to the pair with the circumcircle. There it is. Now, in this case here, the triangle center that is stationary is x3. Let's draw the anticevian triangle of this blue triangle with respect to x3. Here it is. Here's the anticevian triangle. It's something that goes out to the left and right sides here a bit more. So it's a more eccentric triangle in that sense. More spread out. Okay, now it is the anticevian of this family in the sense that if I draw the 3 cevians which pass through x3, okay, if I draw the 3 cevians of the green triangle which pass through x3, I get the blue triangle. So the green triangle, which doesn't have a formal name, is the anticevian of the blue triangle with respect to the point that is stationary, the circumcenter. Now let's draw one of the ellipses, and one of the circumellipses, centered on one of the vertices of this anticevian triangle. There it is. Now let's watch its motion. Its area is variable. Let's draw the 3 ellipses so constructed. Now here's the kicker. The sum of the areas of these 3 ellipses indeed is invariant. Even though each one of the 3 is variable, the sum is now invariant. Okay, now let's look at a third example here. Let's look at the elliptic billiard, the confocal pair. So I'm gonna turn everything off and I'm gonna go to the confocal pair. Confocal pair, also known as the elliptic billiard. It's a triangle family interscribed between 2 confocal ellipses. The outer one, known as the billiard, and the inner one, known as the caustic. They're confocal. Their foci are not shown here, but they share foci. Okay, what is the triangle center of this family, which is stationary over the family? It's the Mittelpunkt x9. It's Mittelpunkt x9. There it is. Let's draw the eccentric, the eccentric triangle to this family. There's the eccentric triangle to this family. It actually has a nice property that this is the only pair where the sides of the eccentric triangle are actually tangent to the outer ellipse, the outer conic, and that's because this family is precisely defined in such a way that at each bounce, okay, each pair of consecutive edges is bisected by the normal to the ellipse. Since the eccentric triangle is perpendicular to that normal, you're going to have this nice situation here where the eccentric triangle is also tangent to the outer conic. Now let's repeat that first construction where we draw one ellipse centered on an eccentric. Okay, let's watch its area. It is variable. Let's watch the sum of the area of the 3 circumellipses so constructed. There they are. Their sum is not variable. Now let's look at our attempt at generalizing this invariant sum. Let's draw the anticevian triangle to the confocal pair with respect to x9. Okay, so this is a triangle, this green triangle, such that its cevians with respect to x9 produce the original 3-periodic in the elliptic billiard. Let's watch this family of anticevian triangles with respect to the center of the billiard, or x9, which remains stationary there. Now let's draw one of the ellipses. Let's remove the cevians. One of these ellipses centered in one of the vertices of the anticevian with respect to x9 has variable area. Let's now draw the 3 circumellipses. Notice that the sum of the areas remains constant. So it looks like we have a nice rule here. you take a concentric Poncelet pair, you figure out what's the anticevian triangle with respect to the center of the pair, common center, and then you draw the three circumellipses centered on the vertices of that anticevian triangle with respect to the center of the pair. And what you're getting here is an invariable sum of circumellipse areas. There is a fourth example that is neat but is more trivial, and that's the homothetic pair. Let's look at the homothetic pair. There it is. Let's scale that up. The homothetic pair is a family of triangles interscribed between two homothetic, axis-aligned, concentric ellipses. It is in a way the affine image, right, of the concentric pair. Here's a concentric pair. I can just stretch this guy in whichever direction. Let's stretch it in the x direction. So we're going to take this family of equilateral triangles, interscribed between two concentric ellipses. We're just going to stretch it along, say, the horizontal axis, and we get this new family. This family conserves area, and all of these are consequences of it being an affine image to the concentric pair. Now, what is the anticevian triangle with respect to x2? That's precisely something called the anticomplementary triangle. The anticomplementary triangle is a triangle which is the anticevian triangle of a triangle with respect to x2. Okay, so the cevians passing through x2 of the anticomplementary recover the reference triangle. Now let's do one of the ellipses centered on one of the vertices of the anticomplementary triangle. The anticomplementary triangle, it's well known that it is similar to the original triangle. It has 4 times the area. So for example, this vertex here corresponds to this vertex over there, and you can think of this green triangle here as being a reflected 4-time area version of the original blue triangle. But what we want to see is that what is a circumellipse centered on one of the vertices of the anticomplementary triangle? Okay, so there it is, this orange thing. Let's animate this figure because we're in for an apparent surprise. Okay, here we go. So I'm animating that. Now check out what's going on with the area of the circumellipse. For the first time, we see a circumellipse whose area is constant over the family. Let's draw the 3 circumellipses. First of all, let's check if our conjecture that if we do this construction with the vertices of the anticevian, we get a constant sum of ellipses, of circumellipse areas. We see that this is being confirmed here. Okay. However, we're getting something extra here. The 3 areas are equal and invariant. So of course the sum of the 3 is invariant as well. Well, this when I first saw this, I was pleasantly surprised, but later realized that this is just a consequence of the fact that this system here is an affine image of the concentric circle system. So ellipses are uniquely defined by 5 constraints, right? So when I stretch the system out to the along the x-axis, the new circumellipses are going to have to pass through affine images of the original vertices and an affine image of the original anticomplementary triangle, which is equal to the excentral triangle, right, in this case, in the A equals 1, B equals 1 case, in the concentric case. But the fact of the matter here is when I finally distort everything, you get that the 3 vertices are invariant under the affine transformation, and the 3 vertices of the anticomplementary triangle, or the anticevian with respect to x2, are also invariant under the affine transformation. Therefore, these 3 ellipses are going to be affinely invariant as well. And since the affine transformation preserves area ratios, they're just going to maintain areas which are constant and affinely related to the original areas. So if you take, for example, the original areas here as being, let's take the original ellipse or the original concentric pair. I'm just going to put it here, and you can see here that I have a perfect circle. The area of one ellipse here is 9.42, give and take. Okay, well, let's double A here. You get twice the area for each one of the ellipses. So if I stretch this whole system by a factor of 2 along x, the area of each one of these 3 ellipses is going to be stretched by an identical factor of 2. And by virtue of this affine transform image, the area of the 3 ellipses in this case stays constant. Okay, but the other 3 examples are not affinely invariant, so you're truly getting something that I would say is non-trivial. So if we go, for example, to the confocal pair, just review that, and I perform the construction on the confocal pair, okay, of the 3 ellipses. Let's take the cevians out. With respect to the vertices of the anticevian, with respect to the origin, I get that their sum is invariant, as you can see here. Okay, so this is not this is not a corollary of any sort of affine transformation. There's truly something nonlinear going on here. But at least it looks like we were able to generalize the property that we had seen in the previous video to other concentric Poncelet pairs. So 2 questions remain. Is this provable, first of all, for the cases that were shown here, with the exception of the homothetic, which is trivial, or the first 3 cases, confocal, in-circle, and circumcircle Poncelet pairs? Is this manifest itself in any concentric Poncelet pair? Is a second question. And are there higher end generalizations for this? Okay, so I hope you enjoyed this video. Thank you very much.